Yeah, everyone, class recording is in session. I'm just gonna quickly share screen with you, Magdalene, so we can recap on what we discussed last time. Ne? So I'm gonna share screen and share that Jamboard from last week. So last week and the week before I wasn't well, so we didn't really have class.
Yeah, I heard about that. What was wrong?
I had a flu, so, and that apparently happens a lot. So I guess it was my turn
You should
to
go
get
check
flu.
it out.
It's cured now, so I don't have anything. Just maybe phlegm. You know what phlegm is, right?
Yes. I heard it when you were trying to speak.
Yes. Phlegm. It's written PHLEGM. Phlegm.
Whoever
Phlegm.
decided that words together create a word called phlegm, that guy.
Letters together create a word called phlegm. Yeah, it's just how English is. It's not really our language, but
it's actually words, because phlegm, you can spell different types of words with the letters coming out from phlegm.
I suppose. I just want to see.
I feel so alone in the mall. Then I found a home in your hall. Got perks, live for love. When you're late, I found out. Is that what you mean? Grow with me into a dust. When I'm around you, feel it. You just let it fall in love.
You know you're being recorded on YouTube, right? So you can sing all you want, but just know.
Whoever's watching that's like, this child.
Like, hey, who's this guy?
Who's this guy? He thinks he's in the studio or something.
Yeah, so I'll just put it out. Yeah, there we go. So yes, quick recap. I'm gonna need you to click on the next slide, as we move forward. Yeah. So quick recap. We discussed the concepts on voltage, current, and resistance, and we also looked at different circuits, looking at resistors in series and in parallel, voltage in series and in parallel, and current in series and in parallel. Current is usually measured in the direction of flow in the circuit. Voltage is measured in parallel, and resistance you either get as a reading or from the, if it's specified on the resistor itself. In grade 11, we go a little bit deeper into Ohm's law, and we look at ohmic and non-ohmic resistors, and the same concepts of resistors in series and in parallel still features in the discussion. Next slide. Then we did a couple of ohmic resistor calculations from a grade 11 learning guide, and this one is where you have to find the current. And then the second type of example in the next slide would be where you're given one resistor, another is unknown, but you have the voltage in the circuit and the current, and you could find the resistance in that resistor. The other slide, we looked at ohmic resistors in series, and we had to work out the total, or rather the voltage drop across each of the resistors to find the resistance in the third and unknown resistor, as well as the voltage drop at that juncture in the circuit. Then for parallel resistors, just to refresh, the resistance, it decreases, or rather it's smaller as you have more parallel branches, and the current increases, but the voltage remains the same across the different parallel paths. And using that information, you can work out for ohmic resistors resistances that are unknown for parallel resistors, as well as the current in the circuit. You can also work out, the resistance of an unknown if you have the current and the voltage and the one resistor there. We can also look at where we're given the voltage and two parallel resistors and we have to find the current. We can also do those calculations. And then there are parallel networks of resistors which you can substitute as one equivalent resistor, so you don't have the complication of multiple resistors that are in parallel. And from there, we extended the discussion to power and energy. Power being measured in watts and energy in joules, and each of these being expressed differently. So electrical power being the product of current and voltage, which using Ohm's law, you can write either in terms of the square of the current or the square of the voltage. And we applied that in calculations where we'd find the power rating on a resistor. We could also do that where we don't even have the voltage, but we've got the resistance and the current. Then also still in a series circuit, applying similar concepts where you have the current, you have the voltage, but you're missing resistance in one resistor, and using that information to find that missing resistance. And we said we'll continue from page 403. All right. So, electric circuits, 399. So let's make that 415. All right. So, we were to continue from page 403. So Tiam, I hope this is a nice revision for you, so that we can get to... So we're just going to look through the worked example in the book anyway. So it's not really like Mr. P's the genius. I wouldn't call myself genius. I'll have to be called that by an authority. Then I'll accept that. But I'll admit my strengths when I see them. Magdalene, Linda, my network is sokodising today. I just want to see on Studio how much more time. Oh, and because YouTube is not open, it's slow to update. Oh, that's terrible. Let's see this one. So 6 August. All right. So so let's say we have a circuit. We're still doing electric circuits. All right. So we're given a circuit in worked example number 11 on page 403 of our grade 11 textbook. So it's Siyavula. All right. And our circuit looks something like this. We've got a battery there, and the circuit branches out into two parallel resistors. And oh no, we did this one. Yeah, we did this one. My mistake. We did it. We finished it. Yeah, so actually that was... Oh yeah, our conversation continues from... So, sorry, I'm just going to scrap this example because we did complete it and the video is also uploaded. So we can always refer to that online. Yes, and that's why I want to capture content. You understand? Yes. So we're going to look at electrical energy. Magdalene, we're still together, ne? Let's first see.
I feel so alone. What the fuck?
Magdalene, we're still together, ne? You can throw a thumbs up into the call. Yeah. So the discussion starts off with when energy is dissipated in a device. Remember, Magdalena, our conversation on dissipation, right? Hey, Magdalene. So during energy dissipation, Tiamo, do you know what dissipate means?
Not really.
Not really. So it's to like break up, right? So, Magdalene?
Trying twice.
Yeah, Magdalene. Opola dissipate, what it means, I get. Waropola dissipate, what the word dissipate means. You remember that, right? From last week's conversation. It's to break apart or to, you see that dam there, Shore Dam.
Mm-hmm.
When you're driving towards Mulechi side, you see like a little concrete wall. Someone even put an advert there that they paint and whatnot. So a lot of structures like that for waterworks, they tend to have things that dissipate the energy of flow of the water. So let's say it's a dam wall here, right? When the water's behind the wall, it has a certain amount of energy, but because it's static, it's not moving. But as soon as that water level rises above the crest of the wall, it moves at a certain energy.
Mm-hmm.
Now, because you don't want it to scour the floor there, you put things called dissipators. Now, that's one structure that looks like that thing that you see when you're driving past.
Yes.
So it breaks down the energy, the kinetic energy of the water so that it doesn't damage the floor below. So dissipation is that action of reducing, breaking down, etc. That's what dissipation means. So I had the same discussion with Magdalene. I just thought I shared with you. But obviously someone who works as a dam engineer would probably correct my theory, but I'm trying to make the approximation to something that you can relate to, that you can see every day.
Cost us.
All right. So when energy is dissipated in a device, energy is transferred from one kind to another, right? Transferred from one kind to another. Now what happens? When a resistor gets very hot, it indicates that the energy is being dissipated as heat. So in other words, let's look at the bars of a heater, right? Mm-hmm. So let's say we've got a heater. I'll just put a grill there and maybe a red line to indicate that the bar is red hot. 2 bars on and they're red hot, right? This is our heater. It's a bar heater. It has electrical energy passing through. And as that electrical energy is passing through, it's a heater. It's hot like a heater. There's a switch. So we have a device there, it's hot like a heater. And it's connected to our mains. So there's the 3-pin plug on the wall socket, ne? Mm-hmm. So we have electrical energy zapping into the system. And there's our electrical energy. It's 240 volts. I don't know how many amps, but let's say this is a 3000 watt heater. That's the power rating, right?
It's too high.
It's too high.
Yes.
Let's make it 2000. 2000?
2020.
2000.
That's the regular temp I know. Voltage, I mean.
The wattage. The voltage is 240
Isn't
if it's AC mains.
Okay, energy is watt.
That's power.
Power.
That's
then
power.
Energy is
Joules
okay.
or kilojoules. All right. So, power. So, okay, what happens here? Electrical energy is dissipated into or electrical power, electrical energy into heat energy, right? So this is what happens. Now, because power is the rate at which work is done, it's also the rate at which energy is transferred. So our definition of power is the rate at which work is done, and therefore rate at which energy is transferred. Ne? So that's what we have now from the discussion so far. But now we also identify another fact. If we want to calculate the total amount of energy, then we need to multiply the rate of energy transfer. So in other words, the power by the time over which that energy transfer took place. So in other words, energy would be the power times the time. So in other words, it'll be watt per second. King, watt times second. So in other words, this is how your electricity meter, whether it's Conlog or HBROS or even ESCOM, that's how they measure the units of power, because it's measured in kilowatt hours, right? And that's a product of power and time. So time is in hours and kilowatt is power.
Is it possible for time to be measured in minutes?
Well, okay, so that's I think that's why our power utilities would measure the units that we buy for electricity in kilowatt hours, because it takes 60 seconds to make a minute, times that by 60 to make an hour, so 3,600 seconds to make 1 hour. And because we're getting quite a significant amount of electricity to power up our devices, then we simply multiply the wattage by 1,000 to get kilowatt. So yes, you can have that time in this instance be in minutes. But for commercial purposes, so in other words, for the sale and exchange of electricity, kilowatt hours seems to make sense. And in our calculations, we started off with watt, which is the basic unit for power, and multiply that by seconds, which is the basic unit for time.
I see.
Yeah, but the dimensions are still the same. We're still dealing with power and time. Oi, question, Magdalene. Hey, Magdalene. Okay, so this energy is also now measured in joules, ne? And it's the same joules, I guess, if you think about it long enough, that used to measure your caloric intake with food. So if you eat a spoonful of margarine for some reason or the other, there's a certain amount of energy that's packed in the margarine that your body's gonna need to burn off by, I don't know, if you shiver or if you run, doesn't matter. But that same concept of joules is similar with the food that we eat as it is with electricity. So in our worked example, we've got, it's worked example 12 on page 409, grade 11 learning guide. We've got a light bulb of 30 watts. So we're given a 30-watt light bulb, and it's left on for 8 hours overnight. So for some reason you were studying from 6 when it starts to get dark, or maybe from 7 when it's darkest in winter. And for the next 8 hours, the light bulb is on. So we need to find out how much energy was wasted. Since how much mtlakase did you waste?
Mama can flip.
Yeah, so that the parents can flip. Like, yeah, I really, you're not studying. You just passed out there and my lights are burning for no reason. So how much energy is, I'll just put it in inverted commas, wasted. So we know that 8 hours is how many seconds?
Second.
Yeah. It's 8 hours times 60 minutes. Eight hours to 60 minutes per hour and 60 seconds per minute. Yeah. So this will cancel that, that will cancel that. And then we've got 8 times 60 times 60 seconds. That gives us how much?
I didn't bring my calculator.
You didn't bring your calculator?
This is bad.
It's fine, we'll just use this one.
To lose my calculator.
So we've got 80 times...
No, it's 8 times 60.
Oh, it's 8 times 60. Yes, that's correct. Times
60 times another 60.
Yeah, so we've got 28,800 seconds, ne? That's how long the light bulb was running for. Now, remember, energy is power times time. Now we need to work out the energy. We've got the power. It is P, and we've got the time. So our power is 30 watt, and our time is 28,800 seconds. And the energy that's wasted is 30 times 28,800. So just say multiply by 30. And we get 864,000 joules, or 864 kilojoules. I'm going to work this out in terms of kilowatt hours, which are the units we use for electricity.
Mm-hmm.
So in terms of units, that would be 30 watt equals 0.03 kilowatt. And we've got 8 hours. Therefore, bulb running for 8 hours and it's 0.03 kilowatt is 0.03 kilowatt times 8 hours, which is 8 times 0.03. That means it'll eat up a quarter of a unit. So if we have a 30 watt bulb, light bulb on, we'll just call it units. I guess that's what it's called when we're buying it.
Yes.
Yeah, we call it units, but the units are kilowatt hours, ne? So if we are going to work out how much 864,000 joules is in terms of, what we use to as electricity units from a power utility company, it's almost a quarter of a unit. So yeah, sure, raise your hand, ask a question, Magdalene. This part here, yeah, units, or this part here, this one. Okay, it's fine, I'll explain again. So I get the part here how we get the time, you understand, ne? Because we multiply the 8 hours by 60 minutes an hour and also by 60 seconds a minute, so that the minutes divide each other out and the hours divide each other out, and then we're left with seconds. So it's 60 seconds by 60 by 8, and then it gives us 28,800. Now the second part is now where we calculate how much energy was actually wasted when the light bulb was left on for 8 hours. So for that time of 8 hours or 28,800 seconds, how much energy was wasted? So we do this. We take the power rating, which is 30 watt, which we are given. Remember, power is measured in watts. And time is measured in seconds. So we're going to focus on the watt, the power rating, and we multiply it by the time. So for us to get the units of measurement of joules, it's simply watt times second, which is joules. And we take the 28,800 seconds, multiply by 30 watts, and we get 864,000 joules, or 864 kilojoules, because kilo is 1,000. Yeah, Koral? Is that clear? It's better, ne? So for fun, I just thought maybe we could calculate that in terms of the units that we use when we're buying electricity from our power utility company. So if you spend 8 hours with the light on and there's no one, and this light is 30 watt, this light bulb is 30 watt, and no one is sitting in there or using that light productively, then if that light is shown or shines for 8 hours straight uninterrupted, then that light bulb will have used 0.24 kilowatt hours. Now we can quickly look at how much that costs your mom or dad or your parents. Electricity tariff, 2024. Let me say household. Household electricity tariff 2024.
8,000 rand.
Yo, that would be something. Eskom's new home flex tariff. Right, so this article is from, wait, let me see. Okay, we're gonna look at two sources of information. The first one is Eskom directly. So let's open that. I think if we open Eskom, we get the information from the horse's mouth directly. So that's always a safe bet. So these are charges for non-local authorities effective from April 1st, 2024 to March 31st, 2025, as well as charges for local authorities from July 2024 to 30th June 2025. Right. So standard fees or charges for services rendered. Let's see what that is. Okay, it refers us to website. Urban tariffs, time of use. Right, so non-local authority charges. I don't know why these are called mega flex and mini flex, but let's just bear with it. So let's just take one non-local authority. Local authority is like Maspal, so I think we should go for local authority. Yeah. Right. Cents per kilowatt hour. Okay. So on this table, we've got prices for in cents per kilowatt hours, and for voltages below 500 volts, which every household is wired with 240 volts. So that would be where we look, right? During peak hours, 634.05 cents without VAT. That's like $6 a unit.
Here, my brother, it's not nice. You can be eating pap plus more vite just because of electricity.
Yeah. So let's look at the numbers. If it costs 634, okay, let's include VAT in our calculation, right? Let's include VAT and say we're gonna pay 729.16 cents per kilowatt hour. So motlakase unit is 7 rand 29 cents. So this is 7.29 rands per unit. Ne? So what's a quarter of that? 3 rand 50 is half of that. So 0.24 times 729.16. So to leave a bulb on for 8 hours straight will cost the household 175 cents or 1 rand 75. So do you see how the money for electricity gets spent, Magdalene? Yeah, Siam, you see now, when you stay up late and you don't use the lights, how much it costs, yeah? So there's always a cost to everything. So with the internet,
This is why my mother's always complaining.
yeah, your mom has very good reason because you're not buying the electricity.
Most of the cases, when I'm in my room and it's time for me to like relax, I usually relax in darkness.
Okay.
But then once I go out into the bathroom, I can keep the bathroom light on for hours.
Uh-huh.
And she'll be like, "Why you turn it on?" I was like, "For whoever wants to use it doesn't have to know the light. They just get in and get out." They're like, "No, class."
Yes.
I'm like, okay. I'm like, I just left it on for a few minutes. It hasn't hit an hour or something.
It's
And
fine.
when I tried to reason with her, she's like, "Ish, when I was on my class, you don't even pay for my class."
Well, you're looking at the numbers now. It's 7 rands for 1 unit.
1 unit.
So those few minutes, they count.
Yeah.
They count. Those few minutes, they count. That one. So don't feel bad that your mom is like, yay, switch off the lights. The parents have good reason. Ne Magdalene, papa, when they say, Timama bone, you understand now why, ne? Eh? It's expensive. It's pricey. It's pricey. All right. So, in another example, worked example, it's worked example 13, and it's on page 410 of grade 11 learning guide. We're given a resistor in a circuit, and it's linked to a battery. The resistor has a resistance of 27 ohms, and the current going through is 3.3 amps. And we must find the energy dissipated in 35 seconds. So we must find that energy. So find energy. So in this case, remember we've got a formula for power, which can be expressed in terms of current and resistance. So we can start there. And this means that the power would be the current, which is 3.3 squared, and we multiplied by the resistance, which is 27 ohms. And this gives us 3.3 times 3.3, which is 10.89.
27. Can I ask where the 27 came from?
Oh, it's the rating for resistance that is given.
And the 3.3?
It's the current that's going through the circuit and through the resistor. Those two are given.
It's dispersed at 35 seconds. Is there any use for that 35 seconds?
So it's just a time-bound challenge where we need to assess how much energy gets dissipated over a time span of 35 seconds. We want to quantify if it's 35 seconds.
Yeah.
I guess similar to when you leave the light on, hoping that someone will get into the bathroom without having to switch them on. How much does that 35-second cost? It's that kind of assessment, you know? Because every second counts. So 10.89 times 27 then becomes 294.03 watts. That's just the power rating. So now, the energy, which is the power rating times time, will be 294.03 times 35 seconds, and that will give us, so we multiply this by 35 seconds, and it gives us 10,291.05 joules or 10,000.29105 kilojoules. We could also do the same example. How much does this cost? Ka-ching! And we convert the time. 35 seconds is how many hours? 1 hour is 60 minutes per hour and 60 seconds per minute. So that means 1 hour is 3,600 seconds. So 3.5 seconds would be how many hours? So 3.5 seconds times 1 hour equals x by 3,600 seconds. And if we divide by 3,600, so x would be 3.5 divided by 3,600. So we just want to quickly assess how many rands or cents that resistor spent over 35 seconds. I agree we are arguing for how it's not a long time. But we just want to see the cost. Right? So we have 3.5. We divide that by 3,600 or 3,000. Oh, no. 3.5 divided by 3,600. 3.5 divided by 3,600. Okay, so it's 1, 2, 3, 4. 9.72 times 10 to the negative 4 hours. That's fine. We know the power is 0.29403 kilowatt. So if we multiply this by 0.29403, we get E equals 123 let's say 0.3 kilowatt hours. So
how come?
1, 2, 3, 10 to the negative 3. So 0.285. You get?
Yeah, I get.
Yeah.
So I thought you just skipped all of the zeros and added a 3 because you felt like it.
I actually was deliberate in putting it as kilowatt hours because it shows that I went to the extent of that one. So roughly 0.3 kilowatt hours, and we want to multiply that by, so let's say 0.3, and we multiply it by 730 cents. 730 unit year 1. So 2 rands for 35 seconds. So it's just below 2 rand 20 for 35 seconds.
I might stay on the moon.
Maybe my math is incorrect. We'll have to get a second or professional opinion. But the goal of showing that there is a financial cost to energy use is important because we need to understand that.
Slappy, do you mind dialing the heat
down? Yeah, sure. Is it burning?
It's roasting me.
It's roasting.
I can even smell my
your skin.
It smells like iron. Like clothes when you iron them. It smells like it's so.
Alright, so I want to finish this one because I believe once we finish it, we come to the chapter summary And I also want to introduce the same concept but for grade 12 so that, you see how all the concepts tie in together. So it's good that we started looking at the cost and now we have a realistic understanding of how much electricity actually costs, right? So in our worked example, it's on page 411 of grade 11 learning guide. So it's called cost of electricity and intentionally so. All right. So, how much does it cost to run a 900 watt microwave oven for 2.5 minutes if the electricity is so we're gonna do the actual cost of electricity, not the one in the book, right? Jamboard. We're gonna do this one here. Yeah. So if the electricity costs 729.05 cents per kilowatt hour, ne? So we know that the power is 0.9 kilowatt, and we know that 2.5 minutes is, so 2.5 times 60, that's 60 seconds, yeah? So this is, 60, 60, 30. So this is 150 seconds. And if we divide this by 3600, we get hours. So this equals 0.0416 hours. Okay. Then the energy will be 0.9 times 0.0416 recurring. So this times 0.9. And this equals 0.375 kilowatt hours. That's crazy. So running a microwave for 2.5 minutes and you're just making popcorn at the time.
Noodles.
Noodles, popcorn.
My grandma, as soon as she hears that microwave go, oh dear, yeah. Get the noodles. Oh, somebody up here but then the microwave is on. Don't do it. Our idea for 5 minutes.
Yes. So Magdalene, you see how expensive our parents have to, how the kinds of expenses our parents have to go through. Yeah. Just to make sure we can light up noodles. So if the cost is 729.05 cents, then per kilowatt hour, then the cost is this. I'll need to multiply it by 7.29. No, man, that's not correct.
I got a question.
Yeah,
about
sure.
These on a calculator. It's an out of box question. Log. What's the use of logs?
Logs, we use them to express things that are exponential.
Such as?
So, like, geez. So this is gonna cost 274 cents. 2.74 rands. Right. So, I'm gonna make an example with something we learned in civil engineering class. When we study soils for their suitability to build as a foundation or as a mixture in some materials, we have to look at the distribution of the particle sizes. So you've got very fine particles which are smaller than 0.02 millimeters. Some are smaller than 0.06 millimeters. And then you've got the 2 millimeter mark and a 6 millimeter mark. And you probably get like a 20 millimeter mark as well as a 60 millimeter mark. So 60 millimeter mark is about the size of a potato. 2 millimeters is about the smaller than the tip of your pen.
Wow.
And 0.06 millimeters, that's like a micrometer. So you can't even see that with the naked eye. So what does that tell you? It tells you that the particle sizes are distributed logarithmically, exponentially.
Oh.
So that's where we can use logs, at least to understand things. Another example, pipe sizes for different piping fittings. It can be in a farm or in a processing plant or anything that uses big pipes.
Yes.
Small pipes tend to cost less, but as the pipes sizes increase, the price increases exponentially, logarithmically.
Eish.
So you increase the size of the diameter by a certain amount of millimeters, then the price goes at least 10x. One. So those are some of the practical situations where we use exponents and logarithms.
Today, as I was asleep in class, I overheard something that my teacher said. He was talking about phasing. He's my physics teacher. He was talking about phasing. So that he said that to phase certain particles of the human body, you have to be vibrating at a certain speed to pass through solid objects.
Oh, that's a very abstract topic. But we'll talk about that after class. We'll talk about that after class. Yo, that's a very abstract topic. Yeah, so electric circuits, now we're gonna go into grade 12. So Magdalene, so far we finished all the work that we needed to learn for electric circuits for grade 10, 11. Now we're gonna start with the grade 12 so that you get an introduction and Siamo starts with his revision because he's now getting ready for the matric exam.
Trial.
Right, so at grade 12, we start off with a summary, right? And in this summary, we need to remember that for current to flow, there needs to be a power source, an electrical source. So an electrical energy source, ne? Electrical energy source. That's the first thing we need to remember. And Magdalene, this confirms everything that we've been talking about. You have a cell, it's connected to a conductor, there are charges from the cell that come from, I guess, the atoms in the battery that are making electrons move. And that force that's moving them is called voltage or electromotive force. Yeah. So, yeah, that whole logic, it all comes down to this. Then a closed circuit. Oh, for current to flow, we need a source of electrical energy. And a source of electrical energy, and a closed circuit. So if we have an open circuit, I mean, your charger doesn't really charge anything if it's in air. It can't charge the air. But once it's connected to the device, then you have a closed circuit. Now, the direction of conventional current. So in other words, conventional meaning everyone has agreed upon this convention. Direction of conventional current ne? Is from the positive pole. Of the cell, and it goes through the circuit to the negative pole or terminal in the circuit. So in other words, if we have a cell and a circuit is closed like that, current flows from the positive, it goes right around and ends up on the negative of the cell itself. So that's what that means. And lastly, the potential difference between 2 points in a conductor is the work done per unit charge. And this moves a positive charge from one point to the other. And this is also measured in volts. So that would be the voltage in the circuit. So what this is explained by, the potential difference is work done per unit charge. And yeah, this is also the energy. Remember, the charge on an electron is the same as the charge that we also focus on in the battery. So that Q sub E of, is it negative 1.9 times 10 to the negative, was it positive 19? Remember that, the charge on an electron?
Negative.
Charge, Magdalene, charge on an electron. Magdalene?
Negative 19, where did that come from? That's negative 9. Wikipedia.
Elementary charge.
You trust Wikipedia?
I mean, it has to be referenced from... It's a quick reference. Yes, the Millikan experiment. Yeah, so it's... So the charge is 1.9 or 1.6 rather. Where do I get 1.9? 1.6 times 10 to the negative 19 coulomb, right? So that's that charge there. Yeah, because remember, the potential difference is the electromotive force. So in other words, the force that moves electrons. So it'll have to do work per unit charge. So that's where we get our potential difference. And it's the same elementary charge that you get from electrostatics and in an electron, in an atom. So that's because in a battery, there's a chemical. So your battery for your phone would be lithium polymer ion. So those ions, because they're charged, there would be a certain charge, an elementary charge on each of those ions.
atoms that are charged are the ones that are constantly moving around.
Reacting. So it depends on like which aspect of science you're looking at. So if you're looking at electrochemistry, for example, where you can make a battery out of a potato,
Yes, that one I know.
you see, or those chemical reactions where redox reactions, or reduction oxidation reactions.
Lemons are best for that one.
Yes. So in that reaction, the electrons that are, or rather the ions that you get in the substance, in the medium, they are charged with that elementary charge. And that's what enables the circuit to close and actually have a flow of current.
So the atoms of the elementary charge, are they moving or are they stuck in a constant position?
They could be, I mean, it depends. Like, I mean, if you've just stirred a solution, if you just stirred a solution of a salt that can conduct now an electrolytic salt, I would like to think that the movement would have to do with if you agitate the solution. That's what I would like to think. But I would much rather advise you think about it as like, I mean, if you have a battery, like a Duracell with like that head and a small claw there, there isn't much movement inside the battery. There isn't much movement of the substance inside the battery. But at an atomic level, that's where you get the movement of the electrons. And now remember, atoms are so small, like very, very, very small, that, and they're also almost 99.999% empty space.
I just don't get that.
So think about atoms in terms of Avogadro's number. Avogadro's number is like 6.2 times 10 to the 24. So if you have 1 mole of substance, you have that many atoms in that 1 mole of substance. And 1 mole, I believe there is a relation between 1 mole and mass of substance. So like if you are going to take remember on the periodic table, we have something that we measure in grams per mole, right? We have something that we measure in grams per mole. So that means if you have 1 mole of substance, let's say you have 1 gram of substance. Then if you have 1 gram of whatever it is that makes your battery run, that 1 gram has 6.2 times 10 to the 24 particles in it.
Yes.
So I'm just making an estimate just to paint a picture. I could be incorrect with the numbers, but
I can see where you're going.
Yeah, but the point is, you get so many atoms, each one of them firing or having an electron that can move in the battery. All right. But ironically, there would be that many particles, fine, but you'll only get like 12 volts of direct current and not even enough to power up a heater. All right. So when you scale that up, you can understand why a power utility like Eskom has to dig up so many mines in Limpopo and Mpumalanga so that we can have the amount of electricity that everyone gets comfortably.
Yes.
And given how that affects the environment, because coal is a one-time use type substance, then an energy mix makes sense. So South Africa is looking at.
Why don't they just use hydro energy?
Hydro.
Yes. You need solar.
And solar, you need large tracts of land, same as
air.
Wind. Hydro, you need deep dams. So the Congo Basin is probably the best place where you can get hydro, because they've got
that huge Viagra Falls.
Yes, they've got hectic.
Is Viagra Falls in the Congo?
No, Niagara, not Viagra.
No, there's a Niagara and a Viagra.
I disagree.
You can check it.
Viagra.
I heard it from a friend today. So like I was like, I didn't know that.
I don't believe that. This is recorded for kids, by the way. No. Nope.
What was he talking about?
There's no Viagra Falls.
It's a chief.
Nope. Nope.
Wait, was this guy talking about a game or something?
It's Niagara Falls. Niagara Falls is in the US.
Niagara, trust me.
Nope. It's Niagara. Yeah, it's Niagara. And it's in between Canada and the United States. Yes, so young man, be careful.
People the bored. Don't want to be in the US no more.
Yeah. So, so yes, where you've got plenty of rivers that can actually have. In fact, between Lesotho and South Africa, we do have a hydroelectric plant. The Lesotho Highlands Water Project, which captures water in Katse Dam in Lesotho, the highlands.
Lesotho is the area that has snow, right?
Yes, where they have Afri-ski.
How is it that they're able to have snow?
Because they are in an elevated mountain range.
I expected you to say that. There are certain areas in South Africa where they also have an elevated mountain range, but then they don't experience snow.
I suspect because the global north is experiencing increasing global temperatures, the global south is also experiencing extreme cold temperatures because the coldest, and this is just my guess. Like, I'm not an expert or anything.
Your suggestion.
It's just my feeling.
Say belief.
Yeah, you can say my belief.
Yes. I don't pronounce on people who say their beliefs because I cannot go against your beliefs.
Yeah, but they can still be argued out against. But the point is, I mean, if the global north is experiencing increased summer temperatures, it makes sense that the global south would experiencing like very low temperatures than the normal. Yeah, so that's my thinking. But anyway, we'll talk about that after class. So anyway, factors that affect resistance of a wire conductor, right?
Yo, we need the factors. Let's go.
So wire conductor is affected by, the first thing is the length. So in other words, if you have a long cable, there's a big chance that the energy will dissipate through the cable. Then there's diameter, how thick the cable is. So if it's a thinner cable, the resistance would be high. And if it's thicker, the resistance would be low. And then there's also temperature. So like the higher the temperature, the greater the resistance, which is why bar heaters and light bulbs tend to get hot and hot and hot. Like a light bulb gets white hot if it's made of tungsten wire, because that wire is thin and the temperature gets super increased. It gets increased a lot. And then lastly, there's the type of material. So tungsten would have a very high resistance, but copper would have a very low resistance.
Why?
It's just the material properties, but that is also why copper is trusted to
conduct electricity.
You open up an extension cord, you find it easy yoga, they break, public connections, they find copper. So
easy yoga.
It's a reality of life in South Africa. So yeah. So yeah, just to illustrate. So yeah, length, how long a material is, the conductor is, how thick or wide, the temperature, as well as the type of material. they become important when it comes to the resistance of a wire or conductor in a circuit. Some revision on Ohm's law.
I was never a fan of Ohm's law.
Why not?
Ohm's law was just, I don't know.
Okay. So in any case, the mathematical formula.
triangle.
Yes.
That triangle, yeah.
The mathematical formula is that the resistance equals the quotient of the voltage and the current. The resistance is measured in ohm. Voltage in volts. And current I in amperes. In amps. All right. Yeah, so then again, like I keep emphasizing, we are looking at revising. Oh, you're still writing?
You can continue.
I can continue. I wanted to change to the next slide. So, just a quick recap. Quick recap. So, we have parallel and series circuits, yeah? Series and parallel. And with a series circuit, you'll typically have, if you have resistors in series, each one has its own resistance that it measures. So here, we've got R1, R2, and R3. And in this case, we've got, let's say R1 and R2. So these diagrams just summarize but also illustrate how we place things like resistors, voltmeters, and ammeters in a circuit, right? So here, the voltage would be different at each resistor. And it's always measured in parallel. And that voltage would be the sum of the total voltage in the series circuit. Okay. And then the second one, where they are in parallel, we could have the voltage here, and it would be different from the voltage here. The ammeter readings might also be different. And also, if you want to measure the current reading, you'd have to do it separate. But the voltage reading would also be measured in parallel. And yeah. So resistors, rheostats, and light bulbs. A rheostat is like a variable resistor, I believe. Let me just check. Rheostat. I just want to check what that is. I think it's a variable resistor. Yes, potentiometer. Yes. So a rheostat, ne? It's like you know the volume knob on your old radio, what's this? Radio electronic devices. That volume knob has got something that looks like that can vary the resistance. So you can change the resistance up and down. So a dial, something that tunes the frequency on an old radio or the volume, etc. That's a type of a rheostat. So those resistors, light bulbs, they are resistors that resist the flow of current. Work done in a resistor is what happens when electrical energy is transformed into heat or light.
I got a question.
Yeah.
Resistors resist the flow of current.
Yes.
So, is there a difference between nullifying and resisting?
So the word nullify means to make something null, and null is like zero.
So to resist, is it same as nullify?
I wouldn't say that, and maybe if there would be a case where resisting is nullifying, it would be an exceptional case. That's just my speculation.
Nullifying, for example, is like this. This car wants to get in the garage with these cars, but this garage is resisting that car from getting in, same as nullifying.
No.
One thing from this side can get to the other side. Am I wrong?
I wouldn't say that's the correct use of the word, but we can always check. Nullify. Meaning. We can always check what the meaning is. To make null, invalidate, to counteract the force or effectiveness of, to make void, to render invalid, to deprive of legal force or efficacy. So
now check resist.
Okay, versus resist. To take an action in opposition to try to eliminate, not eliminate, because to nullify would be to eliminate.
Yes.
To reduce or stop.
Aha.
So it's also synonymous with oppose.
Resisted the effort to close the school. That's a nice example. Because when we read about null, it said to do what? Don't you remember the second one you read it?
Okay, I'll make another tab.
And check the meaning.
Nullify. So to invalidate.
No, this one, the second one.
To counteract the force or effectiveness of.
It means to go against. To counteract, it means to go against. Now open that other one, to resist.
Oh, you're looking at it
to
very
take
nuanced.
action in opposition to. Try to stop.
Try to eliminate.
Try to
reduce
defeat.
Or stop. So in other words,
see, it's taking action to stop.
It's fine, but resistance simply means an attempt to, whereas nullifying is a direct action of.
To contract the
It's
force,
fine.
it means to go against, right? Do you go against to take in opposite action? Doesn't that mean to go against?
I mean,
okay,
oppose. Yeah, I guess.
They still oppose. So
Hey.
what I was trying to say is that, can I write nullify instead of resist?
It depends on who's marking your things, eh? Because now, at the end of the day, you can be smart all you want. And then your script is going to be marked by someone who's just got a marking guideline at the end of the year. So sometimes just be direct. Use what's used.
I miss my English teacher.
No, I get it. And I don't want to say...
Like, she enjoys watching me play around with words.
That's great, but it's always best to stick with what works.
Basic, you mean?
Yeah, unless...
Keep it basic.
Yeah, keep it basic, keep it simple, stupid. That's the best way to get ahead.
Now my teacher, whenever she marks my scripts, she always says, bring your dictionary and follow me to the office.
Okay, so I think we'll end our class here. So from Thursday, when we do physics again, we'll carry on with this discussion and we'll just revise again. Because now it gets nuanced with electromotive force and internal resistance of a battery. So I think those are concepts that are important and specific to grade
Resistors
12.
in a series, do they resist the flow of current, or resistors in a parallel?
We'll discuss that when we look at it in depth on Thursday. Yeah, because it's part of what we sort of covered in the past few weeks. But when we look at it with this in mind, EMF and internal resistance of a battery, then we'll also now expand on those concepts.
Okay.
So we'll end here tonight. Magdalene, do you have any questions?
No.
You are sharp. Okay. I'll see you on Thursday. And yeah, keep well.